In systems theory, a system in a steady state has numerous properties that are unchanging in time. This means that for those properties P of the system, the partial derivative with respect to time is zero. The concept of steady state has relevance in many fields, in particular thermodynamics, economics, and engineering. Steady state is a more general situation than dynamic equilibrium. If a system is in steady state, then the recently observed behavior of the system will continue into the future. In stochastic systems, the probabilities that various states will be repeated will remain constant. In many systems, steady state is not achieved until some time after the system is started or initiated. This initial situation is often identified as a transient state, startup or warm-up period, while a dynamic equilibrium occurs when two or more reversible processes occur at the same rate, and such a system can be said to be in steady state. A system that is in steady state may not necessarily be in a state of dynamic equilibrium, because some of the processes involved are not reversible. For example, the flow of fluids through a tube or electricity through a network could be in a steady state because there is a constant flow of fluid or electricity. Conversely, a tank being drained or filled with fluid is a system in transient state, because its volume of fluid changes with time. Applications. Economics. A steady-state economy is an economy of relatively stable size. It features stable population and stable consumption that remain at or below carrying capacity. The term typically refers to a national economy, but it can also be applied to the economic system of a city, a region, or the entire planet. Note that Robert Solow and Trevor Swan applied the term steady state a bit differently in their economic growth model. Their steady state occurs when investment equals depreciation, and the economy reaches equilibrium, which may occur during a period of growth. Electronics. The electronics steady state is an equilibrium condition of a circuit or network that occurs as the effects of transients are no longer important. Steady-state determination is an important topic, because many design specifications of electronic systems are given in terms of the steady-state characteristics. Periodic steady-state solution is also a prerequisite for small-signal dynamic modeling. Steady-state analysis is therefore an indispensable component of the design process. In some cases, it is useful to consider constant envelope vibration that never settles down to motionlessness, but continues to move at constant amplitude, a kind of steady-state condition. Chemistry. In chemistry, thermodynamics, and other chemical engineering, a steady state is a situation in which all state variables are constant in spite of ongoing processes that strive to change them. For an entire system to be at steady state, i.e., for all state variables of a system to be constant, there must be a flow through the system. One of the simplest examples of such a system is the case of a bathtub with the tap open but without the bottom plug. After a certain time the water flows in and out at the same rate, so the water level stabilizes and the system is at steady state. Of course, the volume stabilizing inside the tub depends on the size of the tub, the diameter of the exit hole and the flow rate of water in, since the tub can overflow. Eventually a steady state can be reached where the water flowing in equals the overflow plus the water out through the drain. A steady state flow process requires conditions at all points in an apparatus remain constant as time changes. There must be no accumulation of mass or energy over the time period of interest. The same mass flow rate will remain constant in the flow path through each element of the system. Thermodynamic properties may vary from point to point, but will remain unchanged at any given point. Electrical engineering. The ability of an electrical machine or power system to regain its original, previous state is called steady-state stability. The stability of a system refers to the ability of a system to return to its steady state when subjected to a disturbance. As mentioned before, power is generated by synchronous generators that operate in synchronism with the rest of the system. A generator is synchronized with a bus when both of them have same frequency, voltage and phase sequence. We can thus define the power system stability as the ability of the power system to return to steady state without losing synchronism. Usually power system stability is categorized into steady state, transient and dynamic stability. Steady-state stability studies are restricted to small and gradual changes in the system operating conditions. In this we basically concentrate on restricting the bus voltages close to their nominal values. We also ensure that phase angles between two buses are not too large and check for the overloading of the power equipment and transmission lines. These checks are usually done using power flow studies. Transient stability involves the study of the power system following a major disturbance. Following a large disturbance in the synchronous alternator, the machine power angle changes due to sudden acceleration of the rotor shaft. The objective of the transient stability study is to ascertain whether the load angle returns to a steady value following the clearance of the disturbance. The ability of a power system to maintain stability under continuous small disturbances is investigated under the name of dynamic stability. These small disturbances occur due to random fluctuations in loads and generation levels. In an interconnected power system, these random variations can lead to catastrophic failure, as this may force the rotor angle to increase steadily. Mechanical engineering: when a periodic force is applied to a mechanical system, it will typically reach steady state after going through some transient behavior. This is often observed in vibrating systems, such as a clock pendulum, but can happen with any type of stable or semi-stable dynamic system. The length of the transient state will depend on the initial conditions of the system. Given certain initial conditions, a system may be in steady state from the beginning. Physiology: homeostasis is the property of a system that regulates its internal environment and tends to maintain a stable, constant condition, typically used to refer to a living organism. The concept came from that of milieu intérieur that was created by Claude Bernard and published in 1865. Multiple dynamic equilibrium adjustment and regulation mechanisms make homeostasis possible. Fiber optics: in fiber optics, steady state is a synonym for equilibrium mode distribution.